This is Kevin Cole at the University of Nebraska. The topic is heat transfer, and the example is measurement of convection by transient surface temperature. Here's the problem statement. You have a device to measure the convection coefficient, which is a polymer test plug, initially at temperature 20 C, coated with a thin liquid crystal layer, which changes color at a particular set point, 25 C. At time 0, the device is exposed to a convection flow at 40 C. If the liquid crystal set point if the liquid crystal changes color at time 3.2 seconds, what's the convection coefficient? We're going to assume that the liquid crystal layer is thin, the polymer is thick, and the heat transfer is one-dimensional. The polymer properties are given here. The solution is going to come from a model, and the number X30B1T0 is how it's cataloged at the website exact.unl.edu. We'll look at that website in a moment. But the solution has the form of a dimensionless temperature is a function of position, dimensionless, time, dimensionless, and heat transfer coefficient, dimensionless. Let me define these quantities. T tilde is the temperature, minus the initial temperature, divided by the fluid temperature minus the initial temperature. The dimensionless position is x over L, and L is the characteristic length. The dimensionless time, T tilde, is alpha T over L squared. Again, that's the L is the characteristic length. And the BO number is the dimensionless heat transfer coefficient, HL over K, where K and alpha here are material properties. And H is the heat transfer coefficient that we are seeking. This is the thing that we're looking for. Now let's look at the exact case. Hang on, has to wait for it to load, I think. There it is. So here is the problem posted, X30B1T0. Here's the geometry, the heat transfer boundary value problem. But here's the definition of the dimensionless variables I was just talking about. I want to scroll through this document and find a plot to get some idea of what's going on. We're looking for the temperature. Here we are. Here's the dimensionless temperature plotted versus time at the surface. Now this is for a particular BO number, but the temperature rises very rapidly, and then the rise flattens out somewhat as time gets large. So this is the interesting bit, is the surface temperature that we're going to be looking for. Okay, here's the document here. I want to talk a little about the characteristic length, L. Characteristic length. It is fixed as we solve the problem, but it's arbitrary. So we're going to solve the problem a couple ways. The first solution is going to be, we're going to choose L. I'm just going to grab a value. Let's say 1 centimeter. Same as 0.01 meters. Then we can go and calculate some of these numbers. The dimensionless temperature now is going to be the set point minus the initial temperature divided by the fluid temperature minus the initial temperature, and that's 5 over 20, or 0.25. The dimensionless position is 0, and the dimensionless time is alpha T on L squared. Alpha from above, here, can we see that? Here it is. It's 1.6 times 10 to the minus 7 meters squared per second. Time is 3.2 seconds. That's the observed time for the sensing application. And the distance we've chosen is 0.1 meters. I'm going to square that. When I compute this number, I get 0.00512. Now, the plot I showed you was for a particular BO number. We're looking for the BO number. So given the dimensionless time and dimensionless temperature, and it's going to be at x equals 0, I need to find the BO number. And the plot is not helpful. Let's look at the solution and find a formula for that. Waiting to load. Okay, so here's the document. I want to find the expression for the temperature. It's page 3. Here it is. Here's the temperature expression. It says the temperature dimensionless has an error function term and this capital U term, which is this guy. So it depends on position, time, and BO number, and the BO number is in this exponential, and it's in this error function. But I'm interested in the surface temperature. I'm going to write this equation down at x equals 0, and it simplifies these relationships a little bit. So let me write that down at x equals 0. So I'm going to have T dimensionless at 0, and time is going to be the complementary error function of 0 minus an exponential of the BO number squared times the dimensionless time times a complementary error function of 0 plus B0 times the square root of dimensionless time. So given these particular values of the temperature and the time, what's the BO number? Well, I really can't solve it by algebra. I really can't solve for B0, but I could plot T versus temperature versus time for several BO numbers. And that's what I've done on the following page. So here's a plot of the dimensionless temperature versus dimensionless time at several different BO numbers. I've got 1, 2, 4, and 8. And the times I'm interested in, locations I'm interested in, again, dimensionless time, dimensionless temperature of 0.25 and dimensionless time of 0.00512. So 0.005 is about this location. Here's the time. And dimensionless temperature about 0.25 is this location. So my crossing point is somewhere in here. So my solution is where those two things cross. It looks like B0 is something like 3.9. This was for graphical solution. I also used a root finder. And I found that the BO number to 4 significant figures was 3.885. So, but the BO number is HL over K. I could rearrange this and say that H must be the BO number times K over L. So that's what I'm going to compute now. BO number is 3.885 using the best value. Conductivity from the previous page for polymer that I'm using is 0.33 watts per meter per Kelvin. Again, I got that from the given values up here. Then the L value that we chose was 0.01 meters. When I compute that, I got H to be 128.8 watts per meter squared per Kelvin. So that's responsive. That's the answer. That's a fairly large value. All right, another way to solve this is to recognize that the exact case has a table of temperature at BO number equals exactly 1.0. Now I'm going to choose L for this solution to be that value for which BO number is 1. Unknown, but I can find it. Now using the table, I'm going to look for the dimensionless time at which the temperature dimensionless is 0.25 at x equals 0, the surface temperature. Let's look at that table, waiting for the other document to load. Okay, let's scroll down and find that table. Here it is. I've got dimensionless temperature at BO number equals 1. All these values in this big table are temperature. And this is the surface. This column here is the surface temperature. At what time is this value equal to 0.25? Well, it's between these two values of temperature is 0.25, and that falls between these two values of time. So let me take these entries from the table, copy them over, and interpolate to find exactly what time represents 0.250. So here's, scroll up a bit, solution B. I'm going to be thinking about pulling out some values of time and temperature at x equals 0, and all of these are for BO number equal to 1. From the table we had 0.07, the value of temperature was 0.24036. We're looking for the time at which the temperature is 0.25, and the other entry that we were close to at 0.08 time, the temperature was 0.25344. And I'm going to interpolate these lengths here. So on the time side, I'm going to have the time I'm looking for minus 0.07 divided by this larger length, 0.08 minus 0.07. And I'm going to compare that to the ratio of these lengths. My first one is 0.25. This is the temperature side, minus 0.24036 divided by this longer length, 0.25344 minus 0.24036. I'm going to solve for t. It works out to be 0.07734. I encourage you to double check my interpolation. Now, at this level, at this value of t, this t tilde is alpha t on L squared, but we know everything in this relationship now except for the length in meters. I can solve for L, which is going to be alpha t with dimensions of t in seconds divided by t tilde, the dimensionless time, and this quantity to the 1/2 power. Let's compute that. L is going to be alpha. The property I'm using is 1.6 times 10 to the minus 7, and that's in meters squared per second. I'm going to multiply that by 3.2 seconds. I'm going to divide that by the dimensionless time here, 0.07734, and all of this needs to be raised to the 1/2 power. When I do that, I get 0.002572 meters. Now this is the characteristic length that makes this true. That was the value I chose. Then I can find, using BO number equals 1, and the fact that the BO number is defined to be HL over K, I can solve that for H. H is going to be the BO number times K over L. BO number is 1. K is 0.33 watts per meter per Kelvin. And this L now is 0.00257 meters. My H then, when I compute that, is 128.3. That's very close, within 4 digits of the value I found with solution method A. This agrees with A. Let's recap. I'm solving a problem associated with a measurement. I'm interested in measuring the heat transfer coefficient associated with the flow. My model is a one-dimensional problem that I can find that exact. We need to understand the dimensionless relationships, dimensionless temperature, dimensionless position, dimensionless time, and dimensionless heat transfer coefficient. We're looking for the Biot number, which contains the heat transfer coefficient. We did 2 solutions. One was we chose the length, and then we had to plot a function. We did a graphical solution, and I also cleaned up that number with the root finder. But then, because the length scale is arbitrary, we used a table of values at a particular value of Biot number, and we looked for a table entry to find the dimensionless time, and then we used that to find the length. And we, again, used the definition of the Biot number and Biot number equals 1 to find the heat transfer coefficient. And if you remember that the length scale for this problem is fixed but arbitrary, then all will be well.